Hello everyone, this is Vijay Raghavan. I am pleased to present our work on differencing-based self-supervised pre-training for scene change detection. This work is done in collaboration with Ilahi Arani and Behram Zanus. Scene change detection is a critical perception task that aims to identify the changes of a scene by observing the scene at different times. They have a wide variety of applications such as urban development, disaster management, and HD maps for autonomous driving. The main challenges in scene change detection are due to the presence of noisy changes in illumination, viewpoint difference, occlusion, and seasonal changes. These noisy changes alter the appearance of the images and makes it difficult to detect the semantic changes that are necessary for scene change detection. Besides the existence of challenges due to noisy changes, deep neural network-based scene change detection methods predominantly hinge on the availability of large-scale labeled images that are expensive and time-consuming to obtain. Therefore, the current scene change detection methods depend heavily on the transfer learning from ImageNet datasets. However, they induce domain shift, which results in drop in change detection performance. To reduce the dependency of scene change detection models on labeled data, we propose a differencing-based self-supervised approach called DSP, which uses absolute feature differencing to learn representations vital for scene change detection. As shown in figure, random transformations are applied to the image pairs T0 and T1 and passed into the Siamese encoder and projection head with shared parameters, producing corresponding representations. To learn the representation of the changed features, an absolute feature differencing is applied over the projection head output to obtain difference representation. Then, a Barlow-Twins objective function is applied on the difference representations D1 and D2 to maximize the cross-correlation of the changed features. In this way, the model will pursue to learn the non-redundant information about the relevant changes that occur between the image pair. Finally, the encoded vectors are transferred to the downstream task of change detection. In this way, DSP uses absolute feature differencing to learn the representation of the change region directly from the unlabeled images while simultaneously incorporating temporal consistency between the image pair taken at different times through an invariant prediction objective and a change consistency regularization. Loss functions. First, we employ Barlow-Twins loss on the difference representation to train the pre-training model to learn representations belonging to the changed region in a self-supervised way. Then, we propose two loss functions to tackle the noisy changes in the images. One, invariant prediction, and the second one is change consistency regularization. Since the invariant prediction explicitly enforces invariance under augmentation between the intra-view features so as to make the predictions of the semantically similar samples to be similar irrespective of the different lighting conditions. We then propose a change consistency regularization to enforce the encoder of the DSP network to elicit similar activations for the image pairs taken at different times. In this way, we incorporate temporal invariance into the DSP model, which implicitly makes the model more robust to noisy changes during the pre-training stage. Experimental setup. We use F1 score metric to evaluate the change detection performance after fine-tuning. We evaluate the pre-training models on two datasets, VLCMU-CD and panoramic change detection dataset. Pre-training performance is evaluated by fine-tuning them using DRTA-net, a state-of-the-art SCD approach. We compare the performance of the DSP pre-training with supervised ImageNet and randomly initialized pre-training, and finally the self-supervised Barlow-Twins model. The table below shows the statistics of the data in each dataset. Table show the performance of the proposed pre-training methods evaluated on the VLCMU-CD and panoramic change detection dataset. The results show that our DSP method can surpass the Barlow-Twins and the widely used ImageNet pre-training on both the datasets significantly. Moreover, it also alleviates the problem of domain shift caused by the transfer learning of the ImageNet weights pre-trained on the datasets vastly different from that of the scene change detection. Finally, these results show the effectiveness of the proposed invariant prediction objective and the change consistency regularization in minimizing the noise due to the significant viewpoint differences during the pre-training stage. The figure on the right shows the qualitative results on the panoramic change detection dataset. This shows that our way of differencing based pre-training can capture more detailed and small changes such as tree branches and pedestrians better when compared to the other pre-training methods. Here, we evaluate the robustness of the scene change detection models on 15 types of natural corruptions and across 5 severity levels. The figure on the right shows the sample corrupted images from VLCMU-CD dataset. On the right, we can see that compared to the ImageNet pre-trained models and Barlow twins, our DSP is more robust as the degradation in performance is gradual when subjected to the corrupted test set. Therefore, DSP brings discernible benefits in terms of robustness to natural corruption compared to the ImageNet pre-training and self-supervised Barlow twins pre-training. Efficiency under limited labels. The availability of large-scale annotated data remains a critical challenge in scene change detection due to the high cost of acquiring label data. Therefore, the scene change detection model needs to demonstrate steady performance when the availability of label data is limited. Figure shows the performance of the different pre-training under the limited label setting. We sample 1%, 10%, 50% and 100% data in a class-balanced manner from the train split and fine-tune the model with a different percentage of labeled data from the training split of VLC-MVCD dataset. Our proposed pre-training DSP outperforms the widely used ImageNet pre-training by a large margin across all limited label scenarios. The drop in performance is more significant when the amount of labeled data is 10% or less, and then it gradually saturates as the availability of labeled data increases. Compared to Barlow twins, DSP increases the performance of the change detection model to a greater extent when the availability of labeled data is scarce and expensive. To the best of our knowledge, this is the first work on scene change detection that relaxes the requirement of large-scale annotated datasets and the additional large-scale labeled ImageNet data. We propose a novel self-supervised technique called DSP that learns consistent temporal representations relevant for scene change detection. Our method DSP without any additional data can match or surpass the widely used ImageNet pre-training that utilizes millions of images. We propose an invariant prediction objective and change consistency regularization to mitigate the effect of noisy changes across a pair of views. Moreover, DSP pre-training significantly improves the robustness of the scene change detection model against natural corruption compared to the ImageNet pre-training. Finally, our pre-training method also demonstrates effectiveness under limited labels and generalizations to out-of-distribution data. Therefore, the findings in this work can be used to increase the performance and robustness of scene change detection where the obtaining the labeled data is scarce and expensive. Thank you for listening. For more details, please refer to the paper.